So this video will be a review of capacitors, which hopefully you remember about from physics, but just in case. A capacitor stores energy in separation of charge. So what you probably remember from physics is you have two parallel plates with a dielectric material between them, and you have positive charges accumulating on one plate and negative charges accumulating on the other plate, and that's where you get your energy storage via the electric field between the two plates. We are not worried about that in this class. There's an equation based on that dielectric constant in the area that gives you the capacitance. We are just assuming we have a capacitor, circuit symbol for a capacitor. It's related to what it looks like physically. It's two parallel plates, and we measure capacitance in units of farads, where 1 farad, abbreviated F, is equal to 1 coulomb per volt. But again, when you are building a circuit, you just buy or look for capacitors that are rated in farads. You're not actually worried about the details of what's physically going on inside them. The equation that governs how a capacitor behaves is I current equals C, so C is our capacitance. In farads, be careful not to get that mixed up with C, the unit coulombs. So in this equation, C is capacitance in farads times dV dt. We can also write that in integral form. V of t equals 1 over C integral from t naught to t I of t prime. T prime is just our dummy variable in the integral. dt prime plus our initial condition v naught. So there are our two equations that govern the behavior of a capacitor. If we look at those equations, we can figure out a couple useful things when analyzing circuits. First is that in steady state, so time is approaching infinity, things are no longer changing, meaning our derivative, dv dt, is approaching zero. So in general in engineering, when we say steady state, we mean things aren't changing, your derivatives are zero. In this case, that means dv dt equals 0, which according to our equation up there means I equals 0. So that's just looking at this equation. If dVt is 0, then I has to be 0. That means that in steady state, a capacitor acts like an open circuit. So no current can flow through an open circuit. So that's like saying that in steady state, if I have a capacitor, I don't care what else it's connected to in the rest of the circuit. In steady state, a capacitor is just equivalent to an open circuit. So I know that there is no current flowing through there. However, I can have a voltage across an open circuit. Okay, so I don't know what that voltage is. That does depend on what's connected to the rest of the circuit. And again, this is something that tripped a lot of people up on the concept exam, seeing an open circuit and assuming that means the voltage across it is also 0, or the voltage down at this point has to be 0. That's not necessarily true. What you do know for an open circuit is that the current is 0, so no current can flow across there. So in steady state, a capacitor acts like an open circuit. Another thing we can figure out from this equation is continuity. So say that I have a graph of voltage versus time over a capacitor, and I want to have an instantaneous jump in my voltage. My voltage just jumps from one point to another like this. So at that point, the derivative of my voltage is infinity. I have dV dt equals infinity. That is going to mean, again, from my equation, that I equals infinity. So in terms of thinking of things that can physically happen, we've talked about how you can't get infinite current out of a battery or a practical power supply. You're not going to get infinite current into a capacitor somehow. And you could also think about this in terms of energy. If P equals IV, then that means getting an instantaneous jump in voltage over a capacitor, if it requires infinite current, that means it requires infinite power. So we can't get infinite power, so that what this is telling us is basically that this can't happen for a capacitor. We cannot have instantaneous jumps in voltage, or else the derivative of your voltage is infinity, and your current is infinite, and your power is infinite. So what that means is that voltage must be continuous over a capacitor. So I have a graph, voltage versus time. The slope doesn't have to be continuous. Okay, I can have a triangle wave, for example, or a sine wave or whatever, but there's no jumps. The voltage is always continuous at every point. That does not necessarily have to be true for the current. So that's voltage versus time. I can have jumps in current over a capacitor, but that doesn't make anything infinite. If I look back at my equations, okay, there's no di dt in this equation, so having an infinite slope for the current doesn't cause me to have infinite voltage. It's the other way around. Infinite slope for voltage causes me to have infinite current. So this is okay. I can have a jump in the current, but this is not. I cannot have a jump in the voltage, which means voltage has to be continuous.